thanks very much for the invitation to speak and to take part in these conferences. And yeah, I'm sorry I can't be here for longer. I'm only here for half this week and half next week. But
recording in progress.
Okay, well, that doesn't need to be recorded, but thank you for the invitation. All right, so the goal is to discuss joint work in progress with James Newton and Juan Esteban Rodriguez Camargo. And the point of this project is to try to compare two different definitions of ordinary p-adic Siegel modular forms. One defined using completed cohomology and one defined from the coherent cohomology of Shimura varieties. And I'm just going to start with some background / motivation from the case of the modular curve. So just for this section, I'm taking G to be GL2 over Q, K, sufficiently small, compact open subgroup of the finite adelic points of G. And then I look at the modular curve over Q inside its minimal compactification. So over here, there's a universal family of elliptic curves. Let's say I call this map F. I call the identity section E. Over this modular curve, and also extending to the compactification, you have an automorphic line bundle that can be obtained by taking the pullback of the sheaf of relative differentials. And so this is automorphic in the sense, well, okay, so its sections give rise to modular forms. And it extends to SK star, partly because this extends to a family of semi-abelian schemes. So if I look at H0 over SK star, and I look at sections for, say, K at least 1, with zeros at the cusps, this is the space of cusp forms of level big K and weight little k. It has an action of a spherical Hecke algebra that consists of Hecke operators, Hecke operators away from finitely many bad primes. Okay, so that's one way to realize modular forms or cusp forms is through coherent cohomology. Another way we saw in Eugen's talk earlier, namely, you can take a local system coming from the relative cohomology of this universal family, the relative, say, étale cohomology. So this is already the local system that's well suited to p-adic interpolation. So I'm going to take nu k, this is k symmetric power of R1 F lower star ZP. So already a p-adic local system. All right, and then you can also view, say, cusp forms or modular forms as contributing to the étale cohomology, say with compact support of SK with coefficients in this local system. And so this also sees some modular forms of weight k and level big K. All right, and the way that you compare them when you're in fixed weight and level is through the Eichler-Shimura decomposition. And I really want to use kind of the p-adic version of this. So I want to write down what's known as Folting's Hodge state decomposition. So you compare these two different cohomology theories. And in order to do that, you need to extend scalars. In this case, I'm going to fix my prime P and take the p-adic completion of an algebraic closure of QP. And just for now, I'm going to extend scalars to this. So in the middle, you can put étale cohomology of SK with coefficients in this local system, and then extend scalars to C. And then this fits into a short exact sequence where on one side you have H0 with coefficients in differentials tensor omega k. This ends up via the Kodera-Spencer isomorphism to identify with omega k plus 2 and then with zeros at the cusps. So this space will see weight k plus 2 cusp forms. Here k is at least 0. And this surjects. And so I've base changed, everything is base changed to C here for this coherent cohomology. And then the kernel ends up being essentially some kind of Serre dual to a space of modular forms of weight k plus 2. But you can write it as a higher coherent cohomology group. So H1 SKC star omega minus k, again with zeros at the cusps, and then with a tape twist. Okay, and this short exact sequence is Galois and Hecke equivariant. All right, but both this étale cohomology, this with p-adic coefficients, and these coherent cohomology groups vary nicely in families. So of course, there are also versions in families of this kind of decomposition, like p-adic Eichler-Shimura. And the particular theorem that I want to generalize in this case of the modular forms is due to Ota. So I'll just say about, 25, 30 years ago, Ota established an integral version of this sequence of this short exact sequence for families of ordinary p-adic modular forms. So in particular, say in these families, you're varying the level, specifically the level at P. I mean, I can say K, but really what you really want to vary is the level at P and the weight. And just as a comment of why this sort of thing is useful, so notice that over here, K is at least 0. And so in this étale or Betti cohomology, you only see regular weight modular forms occurring. And so here you see weight at least 2. That corresponds to that. And then this is dual to modular forms of weight at least 2. So irregular weight doesn't show up in this picture. However, when you're working in some family, you can also specialize to irregular weights. And then suddenly, if you replace this with something like ordinary completed cohomology, which I'll tell you in a second what it is, you have access also to modular forms of weight 1. Okay, so the goal for this talk is to generalize this result of Ota to the case of the group GSP2G over Q. So kind of long-term goal might be to generalize to other Shimura varieties, but I'll explain why this is specifically in the case GSP2G, something within reach. So specifically, the case where the original group is GSP2G, the corresponding Shimura varieties are Siegel modular varieties, and then we're looking at ordinary p-adic Siegel modular forms. And I should say that there's, of course, a lot of related work, but specifically in this integral case, so where you would say tensor over OC, the ring of integers in C, rather than just rationally, there's work of San Giovanni and Skinner in this Siegel case. And they generalize these two maps here, but it turns out that when you go to this higher rank group, suddenly there's a lot more pieces that can fit into the picture, and I want to try and discuss all the pieces that you would expect to see. And then, so this is integrally, and then of course there's a lot of work rationally, so I might not name everyone. But rationally, p-adic Eichler-Shimura maybe started with work of Andreatta, Javica, and Stevens, and work of Chojecki, Hansen, Johansson. And then there's been various generalizations, so rationally in the finite slope case. Work of my collaborator, Juan, Esteban, Rodrıguez, Camargo. This p-adic Eichler-Shimura also shows up in the work of Boxer, Caligari, G, and Pilloni on modularity of abelian surfaces. So there's lots of things, and of course the work of Liu Pan goes even beyond the finite slope case and tells you a lot about the structure of completed cohomology, but rationally. Okay, but really I want to think about this integrally. Okay, there's also, and I apologize if I forgot to name someone. Yeah, let me know. And as motivation for why I specifically want to work integrally is, I'll say that I'd be interested in seeing whether there is an L equals P analog of these kinds of generic vanishing of torsion results for the cohomology of Shimura varieties. So generic vanishing of cohomology of Shimura varieties with torsion coefficients. There's some sense in which you could say that this ordinary condition is at L equals P is some kind of analog of the genericity condition when L is not equal to P. And for instance, kind of for automorphic representations, they're both related to temperedness. Okay, and also this sort of thing should have applications, say, to the study of Euler systems or Iwasawa theory. And finally, I guess I don't need to really write it down, but for me, one motivation was just to kind of understand what should be the definition of an ordinary p-adic automorphic form. Are they, yeah. There are kind of two natural definitions one can give that I'm going to tell you about next. And do they detect the same thing? I guess if you believe, I don't know, the Fontaine-Mazer conjecture, maybe you can accept that, but it would be nice to just see it already on the automorphic side. Okay, so that's the next. So I'm telling you what kind of the goal is, and at some point I'll state a theorem. But before I get to that, I want to tell you how to generalize first the term in the middle of this short exact sequence, and then the terms on the side, how to get ordinary families from these. And I'll start with the kind of easier one, which is to use ordinary completed cohomology. And this is pretty old as a construction. Goes back to the work of Hida, but then was given a more conceptual, say, representation-theoretic interpretation by Emerton. And I'll explain Emerton's construction. I guess at this conference already we've seen completed cohomology quite a bit. right? So in this setting of higher, so from now on, my group is always GSP2G, and my Shimura varieties are always Shimura variety, Siegel modular varieties. And then what you want to do is take the Shimura variety at some finite level, but then take a co-limit of its étale cohomology with, say, mod p to the n coefficients as the level at p gets smaller and smaller. And just to comment, maybe this has come up a lot this week, but maybe for non-experts. So the point of, maybe I'll say here, yeah, the point of going to this deeper level at p is that you can suddenly access different weights as well, because you end up trivializing these local systems that come from algebraic representations of your group. At p, you trivialize local systems like, you know, this new k, or higher dimensional, something coming from, you know, yeah. So you trivialize something like this. Because these are defined in terms of algebraic representations of your group. So this object has access to different weights. So maybe I'll call this R gamma with compact support, Z mod p to the n, and I put a tilde. This is just my definition. To actually get completed cohomology, you have to take a p-adic completion. And this is just inverse limit with respect to n of the previous object. Okay, so this is a p-adically admissible representation of GQP. It's shown up a lot in this conference already. But what I want to do is sort of take maybe the simplest part you can hope to understand, which is the ordinary part. So this is the full completed cohomology, the full representation of GQP. And then we apply to it Emerton's functor of ordinary parts, which is like an integral Jacquet functor in this L equals P case. And I just need a bit of notation. So you can take ordinary parts with respect to an arbitrary parabolic, but I'm just going to focus on ordinary parts with respect to the Borel. My group is split. So I write the Borel as this product of a torus and a unipotent part. And then I denote by n0 the ZP points of the unipotent part. And then the way that you construct ordinary parts, or the way that you apply ordinary parts in general to, say, a p-adically admissible representation of a p-adic group, is you take group cohomology, continuous group cohomology, to it. So in this case, I'll do it to the mod p to the n object. Then you invert Hecke operators. So these are Hecke operators that are double coset operators corresponding to elements inside the QP points of the torus that are very regular. And roughly what you need is you need to know that conjugation by this kind of strictly contracts this p-adic group, n0. Okay, so you invert all these Hecke operators, which just act kind of functorially on group cohomology by kind of you conjugate and then you apply a co-restriction map in group cohomology, but you invert them and then finally you take a limit with respect to it. Okay, and sort of the outcome is a p-adically admissible representation of just the QP points of the torus, and I'm going to call this R gamma with compact support and 0 ZP ordinary. So just by properties of the ordinary parts functor, if you start out with something with reasonable finiteness properties, you still get reasonable finiteness properties. And maybe I'll just mention that there are some subtleties about this in this higher dimensional setting. For example, this is a priori concentrated in degrees from 0 to twice the dimension of the Shimura variety, but you can prove that this is actually concentrated in degrees from 0 to the middle degree. So this is the dimension of the Shimura variety. This is a theorem that I proved in joint work with Dan Galota and Christian Johansson, maybe, I don't know, a number of years ago. 7 or something. But the point is, somehow you need to use perfectoid Shimura varieties in order to prove something like this. So this is still, in this higher dimensional setting, something concentrated in a number of degrees, and you can kind of cut down a little bit, but it's not enough to get these kinds of generic vanishing results at finite level. Okay. No, I don't think it depends. No. I mean, ultimately you can conjugate. Yeah. Okay. So this is going to be one player, one thing that you see in the Eichler-Shimura decomposition theorem. The other thing is much more recent and much more subtle to construct. So I'm not going to give you the construction. Sorry, I'm just going to try and figure out how to move these boards. Of course, the other players are going to be the higher Hida theories introduced in this generality recently by Boxer and Pilloni. Yes, sorry. I did exactly the wrong thing, right? Nope. Okay. I guess just to clarify, I could even say if I conjugate it in 0 to something smaller, the fact that I've taken ordinary parts is still going to tell me it's the same. It's isomorphic to the original thing. Okay. So the second way you can construct ordinary families of p-adic Siegel modular forms is higher Hida theory. And so this is something that for degree 0 coherent cohomology was done by Hida a long time ago. And then this was vastly generalized in recent years, maybe 3 years ago in this Siegel case by Boxer and Pilloni. Okay, and something I want to mention is completed cohomology is very general, and ordinary completed cohomology is general too, and you don't even need to have a Shimura variety. But in contrast here, at least for the time being, this is available in this case, this theory of Boxer and Pilloni that interpolates higher degree cohomology groups of Shimura varieties integrally. This is available in the case of Siegel modular varieties, and somehow my feeling is that there is a significant difference between this theory in the case of a group that admits a Shimura variety, where the group is split over QP, and where the group is not split over QP. So that case requires more ideas, although you can ask them. It sounds like they have ideas, but so for me, sorry, I just mean that for me, it is actually important that this group is GSP2n. But really what's important is that I work with a group that's split over QP. Like this is the case where I feel like I understand, and I'll explain why. And I certainly don't understand going beyond that yet. Okay, so. Okay, and just to, before I get to the Boxer-Pilloni construction, the idea that already goes back to Hida and that comes up in the construction of p-adic modular forms is, well, you know, for completed cohomology, we went to deep level at P in order to trivialize our local system. In the case of coherent cohomology, we have automorphic vector bundles like the line bundle omega, and we want to trivialize that. And in order to do that, you first have to restrict to the ordinary locus, or rather the Igusa tower, over the ordinary locus in, say, the formal completion of the Shimura variety along its special fiber. And so the reason that we do this is so that we can trivialize automorphic vector bundle, and so that we can interpolate kind of automorphic forms of different weights. Right, like our omega to the k that we had before. Okay, and so I need a bit more notation. I'm going to take P inside G to be the Siegel parabolic. And this has a Levy decomposition where, say, this is the Levy, this is the unipotent radical. And then it turns out, so what Boxer and Pilloni do is they construct one version of higher Hida theory for each element in a certain relative Weil group. So MW, this is a set of minimal length representatives of Weil group of our split group G, quotiented out by the Weil group of the Levy M. So it's essentially these cosets that control how many higher Hida theories you have. And so I can see the kind of these parameters in two ways from the geometry of the Shimura variety. One way is if you look, say, at the ordinary locus on the special fiber at Iwahori level, this set parameterizes Kottwitz-Rappaport strata, which are components of the ordinary locus where kind of you have a flag inside the p torsion on your abelian variety, and it parameterizes whether you have things like, say, étal, multiplicative, or some other permutation like multiplicative étal. So this parameterizes something like this. Another way to think about it, which maybe came up a bit in Gabriel's talk, is that on the generic fiber, this Igusa tower is parabolically induced from this parabolic. And then as you're taking invariance under something like N0, you're naturally forced to look at the Bruhat decomposition. And then this set parameterizes Bruhat cells. And this is really very natural from the point of view of trying to do something like Eichler-Shimura theory. Okay, but just as an example, in this case of GL2 over Q, this is just the Weil group of G, and it consists of two elements, identity and W naught, right? And for the theorem that's still the Otas theorem, you should think of H0 being the kind of, if you construct a higher Hida theory for H0, that corresponds to the identity element. And then, so it's just usual Hida theory. And then the one for W naught, the non-trivial element in the Weil group is for H1, and that's cohomology with compact support. Okay, and so I'll just, instead of explaining the construction, I'll just give you the upshot, or the, kind of what they give you. So for any element in this set, Boxer and Pilloni construct a higher Hida theory that I'm going to call R gamma W cusp. Like, I want things that will compare to cohomology with compact support. And so that's why I'm considering this version of the theory. And this is built in a similar way to completed cohomology or ordinary completed cohomology with some key differences. So it's inverse limit with respect to n of mod p to the n objects. It's a co-limit with respect to a level at p, but now this level at p is contained inside the QP points of the parabolic. And I'll say, so once I write it, I'll explain why this shows up instead of GQP. And then these are going to be levels that contain our n0. So we only kind of go up to an n0 tower, which would also happen on ordinary completed cohomology, particularly if you think about it from Hida's perspective. Okay, so it's something like this. And now you have to take some cohomology, and this is going to be coherent cohomology of some Igusa tower. But something very important is it's coherent cohomology with some kind of partial compact support that depends on the Weil group element. And then you have an Igusa tower at this level. I mean, there's also a tame level, which stays fixed, k away from p, but more importantly, the level at p varies. And this is over, say, z mod p to the n, and then with coefficients in sort of the ideal sheaf of the boundary divisor. And then you take some ordinary parts with respect to some Hecke correspondences that get twisted by this element W. So what's really important is how kind of each element W determines the version of higher Hida theory that you're looking at. And so the most important thing is here you have cohomology with partial support, say partial compact support, determined by W. And also it shows up here in twisting the correspondence. So somehow on different, say, Bruhat cells on the Igusa tower, you might see a twist of your original, say, UP correspondence. And so in the modular curve case, the case W equals identity will correspond to just usual cohomology, taking ordinary parts with respect to the UP operator. That's just, because the Igusa varieties are affine, that's just an H0. And so that's a degree 0 cohomology. That's classic, or like usual Hida theory. But if you look at W naught, then you end up taking compactly supported cohomology of the Igusa tower. That's concentrated in degree 1. And then you take ordinary parts with respect to some twist of your usual UP operator. And so that interpolates this H1 cohomology that you see up there in that short exact sequence. All right, and in general, there's a lot of kind of intermediate support conditions that you have to look at, determined by your Weil group element. So let me just mention that they construct this. This is a representation of TQP, and they prove, so still Boxer Pilloni, they prove that it has p-adically admissible cohomology. So some finiteness result for the cohomology groups of this complex as a representation of TQP. But I'll say that this is much more subtle in this case of coherent cohomology because you're taking this cohomology of this Igusa tower that is not proper. It's much more subtle than in the case of completed cohomology of the Shimura variety, which has a nice compactification that preserves the cohomology. Okay, and they conjecture that this is concentrated in degrees from 0 to LW. This is the length of this Weyl group element, this representative, minimal length representative in this complex. So, degree, if W is the identity, degree 0. If W is the longest Weyl group element, a priori you could have cohomology in degree up to the middle. It ends up just being the middle because of this affineness. Yeah. Oh, I wasn't sure because Gabriel didn't, so really? Okay, well. That makes my life easier. Okay, so maybe I'll tell you the main result. Yeah, thanks for sitting through more than half the talk before. So this is a theorem, as I said, in progress and joint with James Newton and Juan Esteban Rodriguez Camargo. There is a decreasing filtration on, so I take my ordinary completed cohomology, I extend scalars by tensoring with the ring of integers in C, and this is the ordinary one. So I've taken ordinary parts, and then with graded pieces, GRL sum over Weyl group elements of length L inside this set. And then you have R gamma W cusp and tensor over OC, and then with a degree shift of D minus L. Okay, so somehow, this conjectural range gets shifted and it ends up being from 0 to the middle degree. So everything is consistent. And this is TQP equivariant when you twist the TQP action on these pieces in an appropriate way. And I won't write that down for simplicity. For appropriate twists of the action. Okay. Right. So the rest of the talk, I want to give you some sense for what goes into proving this. Are there any questions before I go any further? All right, it's okay if there aren't. Somehow the slogan is, you should think that there are kind of two spectral sequences on top of each other that come into computing ordinary completed cohomology after you've extended scalars. One of the spectral sequences comes from the geometry of the Shimura variety, and specifically the Bruhat stratification on the Hodge-Tate period domain. And one of the spectral sequences comes from doing some integral p-adic Hodge theory. And the nice thing is that when you take ordinary parts, things just become very flexible. One of the spectral sequences basically collapses entirely, and then you're able to actually compute what you're left with on each Bruhat cell and massage it so that it looks like one of these higher Hida theories constructed by Boxer and Pilloni. So I'm going to give you steps in the argument, and then maybe I want to talk more about one of the steps, which was, the one that I found the most confusing. So the first thing is clear. You apply a primitive comparison isomorphism that goes back to Foltings and Schulze. So primitive comparison, almost isomorphism in p-adic Hodge theory. So you start out with the object that you're trying to decompose, extend scalars, and then this is almost isomorphic to some kind of pro-et al. Cohomology on the Shimura variety at level n0, which is really a diamond. Okay, and this is the ideal sheaf of the boundary. And I guess this is technically a compactified thing, say minimal or toroidal, but for simplicity, let me suppress this detail for the talk. Okay, so far, this is an obvious way to start if you're trying to compare et al. Cohomology to some kind of coherent cohomology. All right, the next thing is to use the Bruhat decomposition on the Hodge-Tate period domain to break up this complex over here. So maybe I'll call this star star. So the Hodge-Tate period domain is G mod P, a flag variety, first algebraic, and then turned into an adic space. Right, and then you just use excision sequences to break this up. So the Hodge-Tate period morphism will take you from S infinity, Shimura variety with really infinite level at P, to this flag variety. And this flag variety admits a decomposition exactly parametrized by these elements W. Okay, and so these are the Bruhat cells. And so the comment, so for P1, you could do two things. You could kind of take a, say, open unit disk and its complement, or you could take A1 and infinity. Because you're taking ordinary parts, it doesn't matter. So you can already see the Bruhat decomposition in an algebraic way here, or you can take an analytic Bruhat decomposition pulled back from the special fiber, and somehow the cohomologies supported on each of these strata will not depend on this choice. Okay, so you have something like this. This decomposition is n0 equivariant. So at least say if I took stacks, it would descend. And so I could quotient out by n0 here. I could quotient out by n0 here. And I would still have this decomposition. So I can take pre-images of strata. I get locally closed subspaces here. And then I use excision to break up the cohomology of the full object. Okay. One other thing I want to tell you is that so really the kind of the fixed points for the torus action are going to be the Weil group elements in here. And so each of these Bruhat cells contains the Weil group element, and pi inverse of W ends up being essentially the Igusa tower, thought of as really the perfectoid Igusa tower. Then you take the adic generic fiber and you take a canonical compactification of it. So the thing that's really important, I mentioned that I really feel like I only understand the case of a split group over QP. The way that this comes up is because these Weil group elements are really QP points of the flag variety. So they lie in the ordinary locus. So the fibers here are ordinary Igusa varieties. And so there's lots of different kinds of Igusa varieties that can show up on the general Shimura variety, but somehow it turns out that in the case of a split group, and when you're trying to take ordinary parts, somehow the dynamics of Hecke operators allows you to only look at the ordinary Igusa tower. Okay, so that's a point I wanted to make. And so that one I cannot write on, or I can, okay. Thanks. I mean, at infinite that's a great question. At infinite level, like if I do pi inverse of W, then no, right? This is really, this ordinary Igusa tower is just induced, and all of these are perfectoid Igusa varieties. But if I were to take pi modulo n0 inverse, say of the coset corresponding to W, then this actually does depend. I mean, this is roughly this Igusa tower, but quotiented out by some part of n, some part of W that depends on this. And so if you look at, say, the canonical point, which would be the infinity point on your flag variety, you would see essentially a smooth Igusa tower. If you look at the longest Weil group element, you should still be left with just the perfectoid Igusa tower. And then for all the intermediate elements, it would be something that's, I don't know, superfectoid, right? Kind of there are some perfectoid variables on it and some that are not. And you could describe this precisely in certate coordinates. Right, so the dependence of fibers shows up when you take this quotient, which is something that you need to do to get to ordinary parts. Okay, so I'll just say that the dynamics of UT operators break up this big thing, you know, via excision sequences. Into pieces, say graded pieces that look like sum LW, so the length sum over Weil group elements of fixed length. And then, well, you know, these are locally closed strata, so you naturally see cohomology with some kind of support. And the way that I want to write it is very much reminiscent of Heyer-Coleman theory, also introduced by Boxer and Pilloni. It's kind of like an integral version of this. So it's the cohomology of some overconvergent neighborhood of your fiber. So it's not the fiber at W, but really an overconvergent neighborhood. So this is 0 less than epsilon. And then it's also cohomology with some partial support condition. And so the way that they write it is with support in a closed subset of this one. So it's some smaller, essentially some smaller overconvergent neighborhood. Like in some directions that are given by root subgroups, it would still be radius epsilon, but in some directions, it would be some radius strictly smaller, some epsilon prime. Okay, and then ideal sheaf of the boundary and take ordinary parts. Okay, so one way that you can think of this is some kind of integral version of Heyer-Coleman theory. And one step that I really found very subtle in trying to understand how such an Eichler-Shimura decomposition might work is, well, okay, so you have overconvergent neighborhoods of the fibers, and you kind of lose control. Like I said, I can describe very precisely what kind of this intermediate level in the Igusa tower might look like, but I lose that precision if I have to go to an epsilon neighborhood. And so the slogan for the next term is somehow ordinary is overconvergent, right? Ordinary p-adic modular forms are overconvergent. And so prove some kind of version of this in this setting so that you can replace this thing here with something where you can take, you know, epsilon and epsilon prime to just be equal to 0, right? So you want to find some way to take and if you can do that, then essentially you can go to some formal models, and at least you would get something that's concentrated on the Igusa tower, and maybe inside, instead of this sheaf, you could have some sheaf of nearby cycles, but at least it would start to look like what Boxer and Pilloni construct. And you could hope to understand this sheaf of nearby cycles using p-adic Hodge theory if you are strictly on the Gusa tower and you have some kind of model for what that looks like. Say in the kind of over infinity, this is just a smooth tower. Right, so somehow I think a really key step is to be able to go from over-convergent neighborhoods to really just a fiber at W. Right, find a way to take and sort of look at cohomology with support just on, this pi which is something in the Igusa tower. All right, and then once you manage to do this and you're on the Igusa tower, you have a nice integral model for it, and you do some integral p-adic Hodge theory on it. So you do some computation, or first, I guess, okay, you kind of reduce to something like this, except that instead of just the structure sheaf, or the ideal sheaf of the boundary, you have some sheaf of nearby cycles. So the next step is to show that when you take ordinary parts, a very big part of this sheaf just goes away. So ordinary parts kills most of the degrees of cohomology of this sheaf of nearby cycles. And in fact, it really just kind of doesn't kill kind of one line bundle that's summoned in degree, I think, LW. But in order to prove this, you have to do a computation. And so you reduce to a computation in Serre-Tate coordinates. And then once you're on Serre-Tate coordinates, you can compute using Kosul complexes, say in the way that Bott, Morrow, and Schulze compute the nearby cycles on a torus using the perfectoid torus covering it. So a la Bott, Morrow, Schulze. Okay, so I wanted to maybe give a bit more detail about this step 3 that I said in my view is somehow, I don't know, it was the sticking point for a long time. And here, for this step, we really use an idea that's already in the paper of Boxer and Pilloni. We just adapted a little bit to our setting. So in their paper on higher Hida theory, we use something called dynamical compactifications. And so this, I want to explain it partly because it was the sticky point, and partly because it also gives you a sense for higher Hida theory. So the idea is, say I look for simplicity just on the special fiber at some KR stratum, Kottwitz-Rappaport stratum, corresponding to W in, say, special fiber, so over FP bar. And so some component of the ordinary locus, like for example, where the flag at Iwahori level is like etal multiplicative or something like that. And over it, there's some Hecke correspondence that's determined, it's twisted by W. So it's determined by your choice of W. Okay? And so what Boxer and Pilloni do to prove their finiteness properties and to really kind of show that their cohomology theories are well behaved is they construct some compactification of this. Something proper, and where the boundary is a union of a positive divisor and a negative divisor. Both of these divisors depend on W. And then the positive divisor is in some sense expanded by the correspondence, and the negative divisor is in some sense contracted by the correspondence. And so if I have some sheaf F on some coherent sheaf, say, on this compactified correspondence, and I have some cohomological correspondence on this sheaf, then somehow when you take ordinary parts with respect to this correspondence on cohomology, you can clear poles here and you can clear zeros here. So kind of repeatedly applying the correspondence clears poles along D plus and zeros along D minus. And just to give you a picture of the modular curve case, which I think is instructive, if you've never seen this before, right? I mean, this is a very general picture, and it's all very abstract. And even the model, like these compactifications are constructed by blowups, so it's very hard to imagine it. But in the modular curve case, this simply looks as follows. So in the G equals GO2 over Q, as I said, you have two choices for your Weyl group element. The only Hecke operators that matters is the double coset operator for this one. And then here the correspondence. If I'm not wrong in my normalizations, this one looks like relative Frobenius and identity or some isomorphism. And then a natural compactification. So you should think of this as a component of the ordinary locus at Iwahori level, right? The modular curve at Iwahori level looks like this. So you take the component corresponding to identity and take its closure into the whole Iwahori level. That just adds the supersingular divisor. Right? So this is just the closure of that component. Sorry, this one. I mean, this one as well, because it's isomorphic to it, but okay, and then the point is that in this picture, the supersingular divisor is expanded. And then I won't have time to draw it, but if I were to take W naught, what would happen is I would have identity and Frobenius, and that would change the correspondence I'm looking at, and it would be still the same closure, but then the supersingular divisor will be contracted. And somehow what happens to the divisor, whether you want to view it as a D plus or as a D minus, determines whether you want to take usual cohomology or compactly supported cohomology. Because they prove that essentially cohomology would support here of, so over SW of F, if you take ordinary parts, by repeatedly clearing poles and zeros along D plus, respectively along D minus, this ends up being the same as cohomology, just usual cohomology on the compactification, where you've taken ordinary parts. Except, so in this simple case, it's almost that. In complete generality, you might need to twist a little bit your sheaf by the divisors. For some integer that is sufficiently big, but somehow fixed, that only depends on the geometry. So I think in this modular curve case, if W is the identity, you would just take, so D plus would be the supersingular divisor, D minus would be empty, and N could be 1. And then that would be like a version of classicality that you would prove. Okay, and so for our step 3, we apply an overconvergent version of this argument and this is really the last sentence of this argument, to, so a very big sheaf, which is this sheaf of nearby cycles on our Igusa tower. And so then what happens is that we want to get something strictly on the fiber at W, and over here we might have some over-convergent version. But the problem is in this argument, one needs to twist the sheaf and possibly change the integral structure in it. However, because n is fixed, as the radius of over-convergence goes to 0, in our setting, we end up with some almost isomorphism. So this would be and then I can just take some over-convergent version of the plus divisor and an over-convergent version of the minus divisor. Some over-convergent neighborhood. But somehow, yeah, as epsilon goes to 0, I can show that these things are sort of arbitrarily close. So ultimately, you do get an almost isomorphism. Right, and so you prove everything with almost isomorphisms, and then at the very end, you observe that ultimately what you have is built out of perfect complexes over the Iwasawa algebra, and so you can kind of prove an isomorphism on the nose at the very end. All right, thanks for your attention.